Welcome to homework.
So here we're going to draw the incline. We can draw the free body diagram for the crate. This will be our angle theta. This would be our crate. Perpendicular to the surface of contact would be force normal. And then going straight down would, of course, be force of gravity, so mg. We're going to, for part A, we're trying to find the acceleration. So sigma f in the x direction. Let's apply Newton's second law. This would be equal to the x component of the gravitational force. This would be equal to ma. And we find that the acceleration is then equal to g sine of theta. For part 2, we want to find the time for a displacement of L. So delta x would be equal to L, which would be equal to Vx initial t plus 1/2 of AT squared. And so we can eliminate Vx initial. We know that that is going to be 0. So the time would be equal to the square root of 2 times L over the acceleration, or in this case, g sine of theta. For part 3, we're going to say that the final velocity would be equal to the initial velocity plus at. We know that the initial velocity would be 0. This would be equal to g sine of theta times the square root of 2L over g sine of theta. And so the final velocity would then be equal to the square root of 2GL sine of theta. At this point, we are going to try to find the normal force. Here, we're going to take the sum of forces in the y direction. This is going to be equal to the normal force minus the y component of velocity, mg cosine of theta. This is going to equal 0 because the system has translational equilibrium in the y direction. This would be our Cartesian axis. So in the y direction, this has a translational equilibrium because, of course, the crate is not moving off the surface of the incline. Therefore, force normal would be equal to mg cosine of theta. Now, for part B, they're telling us that the mass now equals 1,500 kilograms. L is equaling 100 meters. And we know that the acceleration, now we can plug these in. So the acceleration now becomes 9.80 sine of theta, and the units here would be meters per second squared. For t, this would equal the square root of 2 times 100 divided by 9.80 sine of theta. The units here would be seconds. For the force normal, this would be 1,500 multiplied by 9.8 cosine of theta, and the units here would be newtons. And then for the final velocity, this would be equal to the square root of 2 times 100 times 9.8 sine of theta, and the units here would be meters per second. And so essentially, we're going to plot all of these as a function of theta. So now plot acceleration as a function of theta, t as a function of theta, force normal as a function of theta, and velocity final as a function of theta. And when we do, these are the resulting graphs. So we have acceleration versus angle, the time to the bottom versus angle in degrees, the final velocity versus the angle in degrees, and then the normal force in newtons as an angle versus the angle in degrees. Now, you want us to check the limiting cases. At 0 degrees, the acceleration and the final velocity should be 0, which checks out. At 90 degrees, the normal, and at 0 degrees rather, the normal force should be equal to the weight, and it's going to be a little bit less than 15,000 newtons, so this checks out as well. And then the time to the bottom at 0 degrees should be approaching infinity, because it should, of course, already be at the bottom. So this checks out because here we have a vertical asymptote at 0 degrees. So here, the 0 degree limiting case works out. The 90 degree limiting case works out as well. The acceleration should be equal to g, the acceleration due to gravity. And as you can see here, it's a little bit less than 10. So this checks out here. The final velocity should be between around 45 meters per second. So that checks out. The normal force should be 0 because there shouldn't be any contact with any other surface. So at 90 degrees, the normal force should be 0 newtons. This works out. And then the time to the bottom should decrease as the angle increases. This works out. And at 90 degrees, the time to the bottom will be approximately 4.5 seconds. That is the end of the solution. Thank you for watching.